We're going to look at the problems from chapter 1. We're going to work them through. Yours are in color and mine aren't. I should probably print them next time on a color one. But you have these pictures. They're in the book. You'll be able to look at them. So what we want to do is look at, there's 3 different pictures. These are red individuals. I think these ones are blue, right? And these are blue and red together. And these are blue and red together. Okay. So under one set of conditions, substances A and B mix. So you mix those 2 together, and the result is depicted in C. Does this represent a chemical or physical change? So what we have here is individual atoms, and all of a sudden now we have them kind of together. They're bonded. So we would say this is a chemical change. Okay. Under second set condition, the same substance mixed, and the result is depicted in D. I kind of feel like they're still together here. So I definitely feel like this is chemical as well. But I feel like what we have here is change, right? Actually, we have changes in both of them. So there's a change in state, which might be considered a something else. Okay, and the third set of conditions, the sample depicted in C changes to that in D. Here to here, that's a physical change, it's change in state. After the change in part C has occurred, does the sample have different chemical properties? Yeah, no. Different physical properties, yes. Still the same substance. Right, so it's defined physical change and chemical change. I didn't leave a lot of room here, right? Physical change retains identity, characteristics, changes identity. Right, so it says passing electric current through molten magnesium chloride yields molten magnesium and gaseous chlorine. So we had magnesium chloride, put a current through it, and became molten magnesium gaseous chlorine. So I would say definitely that's a chemical change. Okay, because it went and changed the substance. They had magnesium chloride, those 2 combined together, became individual magnesium and gaseous chlorine. So it's separated. The iron in discarded automobile slowly forms reddish brown crumbly crust. Okay, so it's going from a different color. So it's going from, let's say, iron, which is gray, into reddish brown. Iron is flexible. Crumbly is definitely not flexible. So we'll say this one also is a chemical change. And this one we have a different color. So I'm sorry about that. So I believe this one's going to be like a green, yellow, maybe it's a red. Let's call it red. And these are blue. Okay, so we can see that here they are. And on the other side of here, we can see the yellows, and they've gone ahead and not combined with each other, combined with something else. So that's one physical change, or one chemical change, sorry. And then we have some of the blue on the bottom combining with some of the red here. That's a, sorry. Oh, I can't really tell that well. I know there's 3 when I looked at mine on the screen. I have to give you a better example. Oh, another one already. These are individual now, so that's another chemical change. And I believe some of these have a blue in there and some of them have a red in there. Pretty sure that's the way it is. So this should be 3 chemical changes. So there's a blue, yellow, individual, probably blues. This one I think is 2 different colors, blue and red. And physical changes occur. Well, I guess these individual ones are the physical changes, right? So these are going to be your blue, so that's 1. I had 3, but now I look at it again, I'm feeling more it's like 2. I wish I had the color. All right. Which shows a physical change? So look and see, we have basically a yellow and the red one combined, and now they're still combined, but they're not all stuck together. So this is a physical change. So A would be a physical change. And then B, which shows the chemical change. Well, these are combined together. Now they're not combined together. See, the yellow and the red are now just yellow and yellow. So that's what we call a chemical change. Which results in different physical properties? Well, both of them. Right? Which results in different chemical properties will just be. Which results in a change in state. That's A. Right? We can see that here it looks like a liquid, and now it definitely looks like a gas. All right, this is the radius of a barium atom is this value. What's its radius in angstrom? So angstrom is when we measure the size of atoms. 1 angstrom literally means 1 times 10 to the negative 10th meter. So it's a distance measurement, right? Length. So what we do is we take 2.22 times 10 to the negative 10th meter times. We set up so we have angstroms on the top and the 1 times 10 to the minus 10 meters on the bottom. So they cancel. We end up with 2.22 angstroms. It says the area of a telescope as a lens is 7903 millimeters squared. What is the area in feet squared? Okay, so we have to have a way to relate millimeters to feet. So I feel like I know some common things. I know that to convert between the metric system and the English system, I know that 1 inch equals 2.54 centimeters. Now you could do this on your own a different way if you wanted to, right? Look it up, how they're related online. You probably have one step. I also know that 10 millimeters equals 1 centimeter. And I know that 1 foot equals 12 inches. So I have a way to go ahead and convert between millimeters into centimeters, and then centimeters into inches, and then inches into feet. Now the issue I'm having is it says squared. So when I do this, what I have to do is square everything. These are really areas, right? So we end up with 1 inch squared equals 144. Sorry, that's not right. Try it again. 1 inch squared equals 6.45 centimeters squared. 100 millimeters squared equals 1 centimeter squared. And then 1 foot squared equals 104, there it is, 144 inches squared. So these are those manipulated. All right, so they only gave me one number, 7903 millimeters squared. So I'm going to use these in the order they gave, millimeters squared, so I needed to cancel. So 100 millimeters squared on the bottom, 1 centimeter squared on the top, and then 6.45 centimeters squared on the bottom, so they'll cancel, all about canceling, whatever it's equal to 1 inch squared on the top, and then 1 foot squared for 144 inches squared. So those go too. And I ended up with 8.51 times 10 to the negative 2 feet squared. If it takes a technician 45 seconds to polish 135 millimeters squared, how long does it take her to polish the entire lens? Okay, well, this is a definition for us for this problem. Okay, it's what we call conversion factor. What it says is 45 seconds is equal to 135 millimeters squared. And we have our initial 7903 millimeters squared. So then we can use it. It relates time and area in this example. So 135 millimeters squared for every 45 seconds. So that's that. Now we have it in time. Our unit's time, so we probably have the right answer, 2634 seconds. Now, technically, these are 2 and these are 3. So if you did any reading on significant figures, which I never seem to worry about too much, you end up about 2600 seconds. It says 2 numbers in front, so I put 2 numbers in front. All right, how many cubic meters of milk are in 1 quart? 946.4 milliliters. Okay, so we have our starting point, 946.4 milliliters. And we've got to get it into cubic meters. All right, so we need a way to relate these. Well, I know one thing, ready? I know that 1 decimeter cubed is equal to 1 liter. That's definition. This is what I would consider to be common knowledge, along with this one too. Centimeters cubed equals 1 milliliter. I consider that to be common knowledge. This one especially. That's when you go to a hospital. Centimeters cubed is cubic centimeters. CCs, they use it. Okay, so that's my relationship between milliliters and liters. What else do I need? Well, I need to get it in from milliliters into meters. So that's true. So we could do that. So let's switch that over. 1 milliliter, 1 centimeter cubed. Right? We'll even draw it on this so you can see it. And then I need a relationship between cubic meters and centimeters cubed. Well, I know that 1 centimeter cube is equal to, let's do it this way. I know that 1 meter is equal to 100 centimeters. That's common knowledge. And I'll cube the whole thing. And with 1 meter cubed is equal to, I think it's 1.0 times 10 to the second. So it's 1 times 10 to the 6 meters cubed. That's right. So then we would set it up so that we had, sorry, this is centimeters, missed it. 1 times 10 to the negative 6 centimeters cubed over 1 meter cubed. And those cancel like that. So then I end up with 9.46 times 10 to the negative 4th meters cubed. And then this one says, how many liters of milk on 835 gallons? 1 gallon equals 4 quarts. 1 quart equals this, 946, right? Well, 1 quart we know is equal to 9.46 times 10 to the negative 4th meters cubed, right? I don't know if that helps us. Okay, so let's see. Let's take a look and we'll do the 1 quart equals 946 milliliters. That kind of helps. Ready? So we'll do 835 gallons times, and we use this conversion factor, 1 gallon, so that it cancels 4 quarts, like that. And then we'll relate quart to milliliters. So 1 quart equals 946.4 milliliters. That's told in our last problem. Okay. And then we have to get it into liters. Now, if we cancel these things, right, we have a milliliter, so we need it in liters. So 1,000 milliliters equals 1 liter, and those will cancel. So we end up with 3,160 liters. All right, let's keep going. All right, so it says a 25-gram sample of each of E3 unknown metals is added to 25 milliliters of water in a graduated cylinders A, B, and C, and the final volumes are depicted in circles below. Given their densities, identify the metal in each cylinder. Okay, so we know that density is equal to 25 grams, mass over volume. Should we have a pretty good feel for that one? And they're all 25 grams, so we know the mass in each one. We just have to figure out the volume, and this is really a volume displacement. So what we're doing is we had 25 milliliters of water, and we added stuff in there. So what we do is this is 26, 27, 28, that's about 20, let's make a guess, 20, it's an uncertain number. So we'll say that our the value is 28.5 milliliters. And this one, 26, 27, 27 and a half, 27.7 milliliters. And this one, we'll say that we have 26, 27, 28, 28 and a half. Maybe that first one's different. Let's see. Hold on. 26, 27, 28. Oh, sorry. It's probably like 28.25. It's a little bit smaller than that. Okay, so what we would do is we take the 25 grams, we divide by how much it changes. So it was 25 to start with, right? So you subtract 25 from each one because we want to see how much the metal displaces the water. Sorry. In each example. So this is 3.5 milliliters. This is 7.7 milliliters. And this is 3.25 milliliters. Okay, so then we shove underneath for A. And we have 3.25 milliliters. What's that, a calculator? And we do it real quick. Let's see. 25 divided by 3.25. That helps if we turn it on. 25 divided by 3.25. It gives 7.7. So A is 7.7 grams per milliliter. And then B, you take that 25 again, divided by 7.7. 3.24. Hang on, that's not right. 2.7. Bad math. 2.7. Let's try it again. So 25 divided by 2.7. 9.26. Let's call it grams per milliliter. And then our last one, 25 divided by 3.5. 7.14. Okay. And I hit that one right on. Good guess, right? So that's going to be the zinc. It's the smallest one, right? And this one's the biggest one, so we'll call it the nickel, although it's not right on, but I had to make guesses based on the measurement. And then 7.87's got to be middle, it's got to be there. Okay, each of the beakers depicted below contain two liquids that do not dissolve in each other. Three of the liquids are designated, A, B, and C, and water is designated W. Okay, so we look at the first one, and we can see that water is on the top, so it's less dense. So water is less dense than A. And then in B, we can see that B is less dense than water, right? And then in the last one, we can see that C is less dense than B. So I kind of get an order here if I want to, right? I'd say that A is the most dense, followed by the water, followed by B, and followed by C. So C is the least dense, based on that information we just drew out there. A is greater than W, W is greater than B, and B is greater than C. So which of the liquids are more dense than water? Okay, so more dense would be A. Less dense would be the other two, B and C. If the densities of W, C, and A are 1 gram, 0.8 gram, and 1.4 gram, respectively, which of the following density is possible for liquid B? Well, we know that B has to be less than water and less than A. So let's see. This one's greater than water. So that can't be one of the options. B actually floats, it's on top of the water, right? We also know that it's greater than C, and C is 0.88, right? So anything below 0.88 wouldn't work. So we have to be this density because it falls between water, which is 1, and C, which is 0.88. B has to be in between those two. That's the only value that's in between those two. All right, an Olympic-sized pool is 50 meters long and 25 meters wide. How many gallons of water, they have the density right here, gram per milliliter. This is a relationship, it's a conversion factor, are needed to fill the pool to an average depth of 4.8 feet. So the first thing you got to do is switch feet into meters, because we have meter, 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 and this is a volume. We know that density is mass or volume. So they want to know, well, I guess I want gallons to start with, right? Just want the volume. All right, so we don't even worry about the density of this one at all. Okay. So let's see. We need a relationship between milliliters and gallons. We're going to need a relationship between feet and meters. So let's do that part first. The 4.8 feet, you'll convert into meters. So let's see. I've just written down. We know that 1 meter is equal to 3.28 feet. If you've ever seen a meter stick, you know this works. So 1.46 meters. Okay? You got that part. So now we can take that 50 times the 25 times the 1.46, and that should give us volume. Length times width times height. So you end up with 50 times 25 times 1.46. And that gives us 1.83 times 10 to the third meters cubed. Okay? So we don't have a relationship between meters cubed necessarily and gallons, but we do have some relationships that make it easier. We know that, let's see, we need no gallons. All right, so we know that we can convert meters cubed into liters or milliliters, right? So we know this is true. 1 decimeter cubed is equal to 1 liter. That's kind of one of those things you need to know, right? And you know that 1 decimeter cubed, 1,000 decimeter cubed is equal to 1 meter cubed. So we know that 1 meter cubed is equal to 1,000 liters. Let's do that. Ready? So we'll take the 1.83 times 10 to the third meters cubed, and we'll multiply by 1 meter cubed on the bottom and 1,000 liters on the top. All right, so those cancel. We end up with 1.83 times 10 to the sixth liters. And now we need to figure out between liters and gallons. So do we have a relation between liters and gallons? Well, I'm pretty sure I can look that up pretty quick, but I have to give it to you because I would never expect you to remember that stuff, right? So let me see real fast. Liters and gallons. Hold on. And we say that we have, let's do 1 gallon for every 1 liter. So 1 gallon equals 3.78 liters. Kind of, you can see that on the urinals in the bathroom when you go to use it. It says it right on there. So anyway, there you go. 1.83 times 10 to the 6th liters times 3.78 liters for 1 gallon. And the liters cancel. So then we end up with 4.83 times 10 to the 5th gallons. Okay, and then it says what mass in kilograms, what is the mass in kilograms of water in the pool? Okay, so I guess we could do it from the liter part of it, right? If we have it at that point. We wrote it down, 1.83 times 10 to the 6th liters. And what we're going to do is we're going to take that 1.83 times 10 to the 6th liter, and we're going to convert it into milliliters. So 1,000 milliliters for every 1 liter, and those will cancel. And then we'll switch it from liters into milliliters into grams. So 1 gram from 1 milliliter, like that. And then we'll switch grams to kilograms, which is kind of it's common knowledge for an AP Chem class. So 1 kilogram is equal to 1,000 grams. And we'll multiply across, and we'll get our number. And I think I had like 1.83 times 10. Sorry, that's bad math. Times 10 to the 6th kilograms. Okay. And I'll stop it for now. So now we're looking at the liquid nitrogen. Okay. So what we have here is liquid nitrogen basically boils at 77.36 Kelvin. Sorry. So anything below 77.36 Kelvin is going to be a liquid form or solid, depending on what the actual melting point is, or freezing point is. But everything after 2773 should be in a gas form. And we know that liquid or nitrogen is a gas at room temperature because it's in our atmosphere. It makes up like 78% of it. Okay, so this one's just going to ask some simple questions. They want a relation between Kelvin and Celsius, which you should know. All right, so we end up with, to get Kelvin, you have to add 273, technically it's 0.15 to Kelvin. That's how they're related. Right. Technically, Kelvin is based off Celsius. And Celsius, we all know, is based on the boiling and freezing points of water. And the point of Kelvin is that we never get a negative number. That's what we want to do. We're trying not to get negative numbers. So if I gave you 77.36, we insert in this equation, we all should be able to figure out that it is, I already worked everything out, negative 196 degrees Celsius. All right. At the boiling point, the density of liquid is 809 grams per liter. That of the gas is 4.566 grams per liter. So liquid and the gas. So the gas is pretty not very dense at all compared to this thing, right? Compared to the liquid. Liquid's a lot closer together, more packed tight. How many liters of nitrogen are produced? 895 liters of nitrogen gas. Okay, is liquefied. So the first thing we're going to do is take the 895 liters of nitrogen gas, and we're going to convert it into mass. And we're going to tell you why in a second. So 4.566 grams per liter. Okay, so then we end up with 4086.5. Let's make it 6 grams. Okay, now this is mass. Mass is conserved. It doesn't matter what state of matter it is. It's always the same mass. Volume, on the other hand, is how much space it occupies. So that can change depending how spread out things are. But the amount of material is consistent. So if we can figure out the amount of material in the gas, then it should be the same as the amount of material in the liquid. And so what it wants is liters of liquid nitrogen gas. We can use this density as a conversion factor like I did here, to convert it from liquids into gas, and then once or grams, sorry. And once I have it into the liters into grams. Once that I have it into the total amount of material present, I can take that amount of material and I can switch it into a volume. So what we say was 809 grams per liter. We end up with 5.05 liters. So if it occupied this much room as a gas, it occupies this much room as a liquid. That's a big difference, right? How much space it needs to occupy as a gas for liquid, because gas has to be spread far apart, so on. Okay. The big thing is here we're using density as a conversion factor. Anytime you have something written above, like miles per hour, right, we end up with a conversion factor. Okay. Following dartboards illustrate the types. Now I feel like when I did it earlier, I couldn't see them, but there should be dots in the middle here. Bullseye represents the actual value, what we want to be close to, and the darts represent the data. So how close to the actual value you get is called accuracy. In case you didn't know that, right? How close they're together, well, that's precision. So usually if you have something wrong with your instrument, you have a problem with precision, because if you're shooting at the same spot over and over again, your sight probably isn't correct on experiment 3. So which experiments yield the same average result? I feel like this is kind of an average towards the middle. This is kind of an average. I'd probably say 2 and 4, because it's kind of spread out around that whole spot. Which experiments display high precision, close together? We would say 3, and we would say 4. Which experiments display high accuracy, close to the actual part it's supposed to be? Well, we would say 4. Right? You're pretty close to the accepted value. Which experiments show systemic error? I feel like that's got to be 3. They're all together. They're precise, but there's something wrong with the actual instrument we're using. All right. Antarctica, almost completely covered in ice, is an area of 5,500,000 miles squared, with an average height of 7,500. So that's how tall the ice and the island and everything is, right? Without the ice, the height is only 1,500. So let's do something real quick. Okay, let's get rid of the, let's get the value for the height of the ice. We'll do that right off the bat, right? It's 7,500 with the ice. It's 1,500 without the ice. So that means 5,000. All right, let's check my math. Sorry, that's just bad math. 6,000. No wonder I was getting the wrong answer. So 6,000. That's B, right? So all my numbers are wrong now. So I got to redo all of it. Okay. What else do we have here? We want the mass of the ice. You have the density, which density is going to give us. It's going to allow us to convert between mass and volume, or backwards. That's what density allows us to do. Okay, so density has mass and volume. So we need to figure out the volume of this piece of ice. Now we have miles squared and feet, right? So we're in 2 different units. So it's probably smart to take that feet and convert it over into miles. So what we'll do is, we know common knowledge, right? 1 mile is 5,280 feet. Did that one wrong too. Okay, so let's see. So we're going to convert that over. So we're going to say we have 6,000 feet times 1 mile, or 5,280 feet, like that. I have 6,000 divided by 5,280. That gives me 1.1, 4 miles. Okay, so I got 1.14 miles, and I have the 5,500,000 miles squared. So if I take these together and multiply them, I end up with miles cubed, which we know is a unit for volume, right? So I'm going to do that. And I get 6.25 times 10 to the 6th miles. Too many loops on there, right? Okay, now I have to figure out a way to take this and convert it over into centimeters cubed. So I need some relationships, right? So I could look up miles to centimeters if I wanted to, right? But if I was on a test, I wouldn't be able to do that. So let's do this. Let's go ahead and write out some things we know. Ready? We want to go miles to centimeters, right? So I know a couple things. Ready? I know a relationship between inches and centimeters. Again, that's common knowledge, guys. You should know that, right? Just as easy as you know this one, you should know the conversion between centimeters and inches. And it allows me to go from the metric system into the English system, which is extremely important. And 1 mile is equal to 5,280 feet. You know, the issue I'm having with this is these are straight up feet, miles, inches. This is miles cubed. So what I have to do is I have to cube all of this. So I'm going to rewrite it. Where am I going to rewrite this? All right, I'm going to rewrite it underneath, under here. So I'm going to cube an inch. I'm going to cube 2.54, which is going to give me, let's see, 2.5. I think I already did this. 1.6. Wait a minute. 2.54. 2.54 cubed. Sorry, one more time. I had it. I just didn't write the number. It's going to be 16.4 centimeters cubed. And then 1 foot cubed is going to be equal to 1,728 inches cubed, right? And then this is the big one, right? 1 mile cubed is going to be equal to, let's see, 5,280, 1.47 times 10 to the 11th feet cubed. All right. So these are my conversion factors. This is my starting volume. So we go 6.25 times 10 to the 6 miles cubed times 1 mile, 1.47 times 10 to the 11th feet cubed, mile cubed, sorry. Then, let's keep it straight. I want to get rid of feet cubed, so 1 foot cubed, 1,728 inches cubed, times 1 inch cubed, 16.4 centimeters cubed. Cancel, cancel, cancel. All right, let's do the math, right? So we already have that. So times 6.25 double E 6 times 1,728 times 16.4. So we end up with 2.61 times 10 to the 22nd centimeters cubed. So that's our volume, but we want the mass, and we have a relationship here, right, with the density. So we're going to take our value, 2.61 times 10 to the 22nd centimeters cubed, okay, and multiply by 1 centimeter cubed, 0.917 grams, right? So it's less dense than liquid water, which makes sense because it's more compact. Divided by 0.917. So we end up with, actually, that's not right, 2.84 times 10 to the 22nd grams. Okay, so that's the stuff for chapter 1.